Hello everyone and welcome to Section 4 of Abstract Modern Algebra. And in Section 4, we will be going over permutations. So, let's look at the definition of a permutation. So, a permutation of a set called A is a function from A to A that is 1 to 1 and on 2, or it's bijective. So we also have permutation groups. So a permutation group, the definition of it is a permutation group of a set A is a set of permutations of A that forms a group under function composition. So we will focus on finite sets. So a neat little fact about permutations used to be the only groups investigated by mathematicians until Cayley introduced the motion of abstract groups in 1850. So the notation that we use to describe permutations is usually we have a symbol. Usually it's a Greek letter alpha, or you may have beta. And then inside these parentheses, you would have your permutation. And then also, we have, now this isn't a matrix, but it does have the same brackets. This is an array form, and that's another way that permutations are written. So let's look at an example. For here, let's make that capital. For the set 1, 2, 3, 4, 5, 6, 7, and the permutation alpha of 1 equals 4, alpha of 2 equals 3, alpha of 3 equals 5, alpha of 4 equals 7, alpha 5 equals 2, alpha 6 equals 6, and alpha 7 equals 1, we can write it as alpha equals 1, 4, 2, 3, 3, 5, 4, 7, 5, 2, 6, 6, and 7, 1. So basically, what this array is showing is it's showing us that the top number is our input, and then the second one is our output. So we have alpha 1 equals 4, so we have 1 going to 4, 2 going to 3, so on and so forth. So, oops. So, let's see. Oops. So, let's see if I can get my pen set up here. Permutations can be composed and composition is carried out from right to left. So, an example. Let's let alpha equal this permutation. And then beta equal this permutation. So then we have alpha beta is, let's rewrite our arrays. So we're going to go from right to left. So notice that we start out beta with 1, and then that goes to 2. So now we will go over to alpha and start at 2, and then that goes to 4. So for 1, we have that maps to 2, which maps to 4. And you can do this for the rest, and then you will find that we get that alpha beta is this array. 1 goes to 4, 2 goes to 3, 3 goes to 1, and 4 goes to 2. And another way we can write this, if we were to write this in terms of composition, we could say that alpha of beta of 1 equals alpha of 2, which equals 4. So this array is our alpha beta once we map all the elements and see what our pattern is. All right, let's change colors here, and we will take a look at another topic. We will take a look at symmetric groups. So symmetric groups are a type of a set A equals 1, 2, and so on and so forth up to n, that has a set of permutations such that the elements have the form alpha equals 1 alpha 1, 2 alpha 2, and so on and so forth up to n alpha n. Or if I can get my pen to show up here, here we go. Or this is saying A maps to A. So the notation that we use to describe symmetric groups, we use Sn where n is a natural number. So let's take a look at an example. Let's take a look at the elements of S3. So one element of the symmetric group S3, we'll let epsilon describe it. And we have 1, 1, 2, 2, 3, 3. And then we have alpha, which is 1, 2, 2, 3, 3, 1. And then we also have beta, which is 1, 1, 2, 3, 3, 2. And then we also have alpha squared, and then we have alpha beta, one, 3, 2. And we also have alpha squared beta, which is 1, 3, 2, 1, 3, 1. So notice we have, let me fix my W. Sorry, trying to make sure I'm using. We have, using the proper English, in choices for our first element, which is alpha 1, and then we have n minus 1 possibilities for the second element, n minus 2 for the third, etc. So we can, let me scroll down here. So we can define the cardinality of Sn as n factorial. So for S3, we would have the order of S3 is 3 times 2 times 1 equals 6. And you can see we have 6 elements up here that are from S3. And let me define that this is our identity. All right, so now we will change topics, and let's change colors here. And we will, let's go with green. And then we will look at a new topic. cycles of permutations. So, a much easier and more common way to write a permutation is to write it in a form called a cycle or cyclic notation. So, an example, let's say that we have the permutation alpha is 1, 3, 2, 4, 3, 1, 4, 5, 5, 2. So we have 1 goes to 3, which goes back to 1. And then we have 2 goes to 4, goes to 5, goes to 2. So if we were to write this in cyclic notation, it would be 1, 3, and 2, 4, 5. Because the way we write cycles is we write the first element where it maps to, and then at the end we don't write the element again, because a cycle by definition it's supposed to repeat itself again, so it's supposed to go back. All right, so the number of elements in a cycle is called its length. So if we look at what we wrote above, 1, 3 is a 2 cycle, and then 2, 4, 5 is a 3 cycle. All right, so that's pretty much all there is to cycles of permutations. Now we're going to look at another topic, but it's kind of related to what we just talked about, or very related to what we just talked about, and it is disjoint cycles. So, for a composition, of two permutations, it is more desirable to write them as disjoint cycles. And disjoint means the cycles have no numbers in common. So let's look at an example. So let's say we have alpha 1, 1, 2, 4, 3, 3, 4, 2. And then we have betas 1, 2, 2, 3, 3, 4, 4, 1. So let's write them in cyclic notation. So we have alpha is, 1, 2, 4, and 3, and then beta is 1, 2, 3, 4. And then let's write out the composition, alpha beta. It'll be 1, 2, 4, 3, 1, 2, 3, 4. So we need to find the in mapping to write in disjoint form. So let's take a look at alpha composed with beta of 1. So we have 1 goes to 2. So we have alpha 2 equals 4. And then we also have 1 goes to 4. Now let's look at alpha beta 4. So we have 4 goes to 1. So alpha 1 equals 1. So we can write that as the cycle 1, 4. Now let's take a look at 2. So alpha beta of 2. So we have 2 goes to 3. So alpha of 3 equals 3. And then we have alpha beta of 3. So we have 3 goes to 4. And then alpha of 4 equals 2. So we can write this as the cycle 2, 3. So our disjoint cycles would be alpha beta equals 1, 4, 2, 3. So what's great about writing it this way is that you don't have as many elements to consider, and you still get the same mapping in the end as you did for this alpha beta. All right, so we can also write this in array form too. So we have 1, 4. So we have 1 goes to 4, which will cycle back to 1. And then we have 2, 3. So this will be 2 goes to 3 goes to 2. So these disjoint cycles in array form would be 2, 3, 2, 4, 1. This is the array form for it. So, one thing to note is most mathematicians prefer to not write cycles with one entry. So any missing element is considered to be mapped to itself. So basically what this is saying is, let's scroll back up here. You see in alpha right here we have 3 goes to 3. So if we were to write that out in cycle form, we could just remove this 3 cycle right here, because we really technically don't even need to write it. So, because it's considered to be mapped to itself. All right. So let's take a look at an example of this. So say we have alpha is this permutation. So if we were to write it in cycle form, well, if we were looking at what we see, we would probably write it like this, but it would just be better to omit those and just write it as 2, 4. Okay, so let's look at the last topic that we'll look at for part 1 of section 4. So, and let's change, we've already changed the pen color, so that topic is going to be properties of permutations. So we will go over some theorems about permutations. So compared to previous sections, the proofs will not be covered here and will instead be shown in part 2. So we're just going to go over, there's a bunch of theorems that we need to look at for permutations, and of course there's proofs behind them too. But for this specific video, we're not going to look at all the proofs. If you want to look at the proofs behind them, then you can watch part 2. That's going to be what part 2 of section 4 is going to be all about, is just the proofs of these theorems. So let's take a look at our first theorem, and that is products of disjoint cycles. So the theorem is every permutation of a finite set can be written as a cycle or a product of disjoint cycles. Next theorem we have is that disjoint cycles commute. So the theorem is that if the pair of cycles alpha equals A1, A2, etc. up to AN or AM, and beta, let's write it down here, beta equals B1, B2, so on and so forth up to Bn, where m and n are integers, and they have no entries in common, then alpha beta equals beta alpha. Okay, so the next theorem we're going to look at is the order of a permutation. Let's try that again. There we go. So the theorem is that the order of a permutation of a finite set written in disjoint cycle form is the least common multiple of the lengths of the cycles. And the notation used for this is often the pi symbol or order of pi. So an example of this, let's say we have the cycle 1, 2, 3, 4, 5, 6, 7, and then 8, 9. So let's define pi as these cycles. So the order of pi is the least common multiple, or LCM, of 3, 4, and 2. These are the lengths over cycles from left to right. That's just going to be 12. Yep. All right, so our next theorem we're going to look at is product of two cycles. So what this theorem is every permutation in Sn, which is our symmetric group, where n is greater than 1, is a product of two cycles. And there's a lemma from this theorem too. And that is that if epsilon, or our identity, equals beta 1, beta 2, so on and so forth up to beta r, where r is a natural number and the betas are two cycles, then r is even. So this kind of leads us into the next theorem that's related to permutations, and that is even and odd permutations. So the theorem is if a permutation alpha can be expressed as a product of an even or odd number of two cycles, then every decomposition of alpha into a product of two cycles must have an even or odd number of two cycles. So if we were to put this in symbols, if alpha equals beta 1, beta 2, so on and so forth up to beta r, and alpha equals gamma 1, gamma 2, gamma s, where beta and gamma are two cycles, then R and S are both even or odd. So let's take a look at an example of this. So let's say we have alpha equals this permutation. So let's write it in two cycles. So we have 1 goes to 2 goes to 4, which goes back to 1. So we can write this as 1, 2, 1, 4. And that's for the first cycle that we have. And then let's take a look at the second one. 3, 5, 6, 7 goes back to 3. So we can write it as 3, 5, 3, 6, and 3, 7. So we have alpha is 1, 2, 1, 4, 3, 5, 3, 6, oops. 3, 7. So we have 5 two cycles. So we can say that alpha is an odd permutation. So the next theorem we are going to look at is even permutations. Capitalize that, form a group. So this theorem states that the set of even permutations in Sn forms a subgroup of Sn. And there is a special name for this group, because it is used often. And that is going to be an alternating group. Now, this is not a theorem, but a new term that's defined, which stems from these theorems. So, the definition of an alternating group is the group of even permutations of in symbols, and it is denoted by a subscript n, where n is a natural number, and it is called the alternating group of degree n. So there is a theorem related to alternating groups, and that is for n greater than 1, A of n has an order of n factorial over 2. And of course, it's denoted as order of A of n. So alternating groups are considered to be one of the most important examples of groups, especially A4 and A5. Okay, so that is it for all the theorems that we're going to look at. So just some closing remarks. Let's see, which color are we going to go with? Let's go with this color. So we have some applications of permutations. So there are several real world applications of permutations, and such examples are rotations and symmetries of shapes, or chemistry molecules. Encryption, solving a Rubik's Cube, and check digit schemes. we will look at some of these in the bonus lectures and examples. Alrighty, that is it for section 4, part 1. So I'm just going to leave a fun little closing remark relating to permutations. So a closing, let's call this a fun closing remark. So let's say that we let T be this permutation, sadness, rest, and learn, happy. And then let's define another permutation, G, and let it be confusion, sadness, math lecture, and learn. So let's say we have a composition T, well, let's take a look at the elements of T and G. So we have confusion, which leads to sadness, which leads to rest. Because if you remember, when we compose, we go from right to left, so we'll look at G first and then see where that element takes us in T. And then we have math lecture. It leads you to learn, which leads you to be happy. So what we can say is, I don't know exactly what your reasons would be for watching these lectures, but let's say that maybe you haven't had too good of a day, or you're confused on this topic. I'll draw both a boy and a girl, because just to represent who could be watching this video. So these are confused and learning. So we could say that they're kind of G, maybe, or at least the first column of G. But then we compose them with TG. And now they are rested and happy. So when we applied this permutation, when they were confused in learning, that led them to feel sadness, which hopefully led them to rest. And then hopefully it led them to want to find a math lecture, which let them learn and which let them be happy. And the reason I say this is I hope that these lectures that you've been watching, and if this is your first time watching, hopefully this video has helped you. Maybe you might feel a little better about this topic. So Thanks for watching. Let's make my smiley face guy seem a little more lively. His eyes and nose were too small. So thank you so much for watching, and hope you enjoyed this video, and I will see you in part 2 if you want to see all the proofs of the theorems. But if not, you can just skip part 2 and go right to the examples and see the bonus lectures for this section 2.